Look at the moon tonight. If the sky's clear where you are, step outside, tilt your head back, and find that pale disk hanging in the darkness. It looks solid. It looks permanent. It has been there every night of your life, every night of your parents' lives, every night for as long as humans have had eyes to look upward. The same face, the same craters, the same grey Maria that ancient astronomers mistook for seas. You have seen it so many times that you probably feel, in some bone-deep way, that you know what the moon is: a rock, a companion, 250,000 miles of empty space away, but always there, always waiting, always real. Now close your eyes. Is the moon still there? Of course it is, you say. Of course the moon is still there. What kind of question is that? The moon does not vanish because you stopped looking at it. The moon does not care whether you're watching. The moon has been circling this planet for 4.5 billion years, long before any eye existed to observe it, and it will continue circling long after the last eye has closed. The moon is not a magic trick. The moon is not a streetlight that flickers off when you turn your back. The moon is matter, mass, gravity, a world unto itself, and it does not need your attention to exist. That is the intuition. That is what every fibre of common sense tells you. And for almost all of human history, no serious thinker would have questioned it. But here is the disturbing part. In laboratories around the world, in France, in Austria, in the quiet basements of American universities, physicists are quietly running experiments that ask exactly this question. Not as a philosophical game, not as a thought experiment to entertain undergraduates, as actual science, with lasers and detectors and meticulous statistics. They are testing whether the properties of objects, including in principle, objects as large as the moon, are fixed and real before anyone measures them, or whether the act of looking somehow calls those properties into being. The results so far have not been comforting. Over the past 4 decades, experiment after experiment has confirmed something that sounds closer to mysticism than to physics. The universe does not appear to have definite properties until those properties are observed. Particles do not have positions until you measure their positions. Photons do not have polarizations until you check. And the experiments keep getting more precise, keep closing loopholes, keep ruling out the sensible alternatives. The weirdness is not going away. The weirdness is, if anything, getting harder to deny. If you have ever heard of quantum mechanics, you have probably heard some version of this strangeness. You've heard that electrons can be in 2 places at once, that cats can be alive and dead at the same time, that the observer changes the observed. But you have also, most likely, filed those facts away in a mental box labelled tiny things. A box that has nothing to do with the moon, nothing to do with the world you live in, nothing to do with the chair you're sitting in or the body you inhabit. Quantum weirdness is for atoms. Quantum weirdness is for subatomic particles. The moon is safe. That too was the intuition, and that intuition is now being tested. In 2015, a team of physicists in the Netherlands performed an experiment so carefully designed that it closed, almost entirely, the remaining loopholes in a famous series of tests called Bell tests. The result was unambiguous. The universe does not contain hidden variables that predetermine the outcomes of measurements. The universe does not have secret instruction sets that tell particles how to behave before you ask. The properties of quantum systems are not fixed in advance. They are, in some sense, that physicists are still struggling to articulate, created by the act of measurement itself. And here is what keeps the most thoughtful physicists awake at night. There is nothing in the mathematics that says this strangeness stops at any particular size. There is nothing that says quantum rules apply to electrons but not to molecules but not to dust grains but not to baseballs but not to moons. The equations do not draw that line. The equations apply, as far as anyone can tell, all the way up. The moon is made of atoms. Each atom obeys quantum mechanics. The moon, therefore, is a quantum object. So why does it look so solid? Why does it seem so real? Why does it not blur into a superposition of positions, a ghost of itself, a probability cloud smeared across the sky? That question has a name. It is called the measurement problem, and despite nearly a century of effort, despite entire careers devoted to the puzzle, despite some of the greatest minds in the history of physics wrestling with it in the most sophisticated ways imaginable, no one has solved it. Not really. Not in a way that everyone agrees on. Not in a way that makes the discomfort go away. If you want to understand what the physicists are really testing, if you want to feel, even faintly, the vertigo that the best of them feel when they think about this honestly, you have to go back. Back before the Bell tests. Back before the loophole closures. Back to a time when physics seemed solid, when the universe made sense, when reality was simply there, waiting to be discovered. Consider subscribing if these late-night journeys help you think or help you drift. A like or a subscribe is always appreciated. Now let us begin. The story opens in 1935 in a small apartment in Princeton, New Jersey. Albert Einstein is 56 years old. He has been in America for 2 years, a refugee from a Europe sliding toward catastrophe. The institute that brought him here has given him a modest salary, a pleasant office, an assurance that he can spend his days thinking about whatever he wants. What he wants, most urgently, is to prove that quantum mechanics is wrong. Not wrong in its predictions. Einstein knows the predictions work. He helped create them. 30 years earlier, he was the one who proposed that light comes in discrete packets called quanta. He was the one who showed that energy is not continuous, that the smooth Newtonian universe is actually grainy at its foundations. For that work, he won the Nobel Prize. He is, in a sense, the father of quantum theory. But the child has grown into something monstrous. The version of quantum mechanics that dominates physics in 1935, the version developed by Niels Bohr in Copenhagen, refined by Werner Heisenberg and Max Born, and a generation of brilliant young theorists, says something that Einstein cannot accept. It says that particles do not have definite positions until they are measured. It says that the act of observation does not reveal a pre-existing state, but brings a state into being. It says that, at the most fundamental level, reality is not deterministic but probabilistic, that the universe does not decide what happens next, but only what might happen, with what odds. Einstein hates this, not because he cannot follow the math. He follows the math just fine, not because the theory makes bad predictions. The predictions are astonishingly good. He hates it because it seems to leave something out, because it suggests that the moon really might not be there when nobody looks, because it violates, in some deep way, his sense of what a physical theory ought to be. "Do you really believe," he asks a colleague one evening, walking through the streets of Princeton, "that the moon is not there when nobody looks at it?" The colleague, Abraham Pace, is not sure how to answer. The question sounds ridiculous. Of course the moon is there. But the equations that work, that predict the outcomes of every experiment, do not quite guarantee it. Einstein decides to force the issue. In May of 1935, he publishes a paper with 2 younger colleagues, Boris Podolsky and Nathan Rosen. The paper is short, only 4 pages, but its implications are explosive. The title is dry and technical. Can quantum mechanical description of physical reality be considered complete? But the argument inside is a dagger aimed at the heart of the Copenhagen interpretation. The paper describes a thought experiment. Imagine 2 particles that interact and then fly apart. According to quantum mechanics, the particles remain connected in a peculiar way. Their properties are correlated, even after they are separated by an arbitrarily large distance. If you measure the position of one particle, you instantly learn something about the position of the other. If you measure the momentum of one particle, you instantly learn something about the momentum of the other. And the correlation is perfect. Not approximate, not statistical, but exactly 1-to-1. Now, says Einstein, consider what this means. Before you measure the first particle, the second particle does not have a definite position or a definite momentum according to quantum mechanics. Its state is a blur of possibilities. But the instant you measure the first particle, even if it is 1,000,000 miles away, the second particle suddenly acquires a definite value. Not because any signal has travelled between them. Signals cannot travel faster than light, and the effect is instantaneous. Not because the second particle was already definite all along. The theory explicitly says it was not. The effect seems to require that your choice of what to measure on the first particle somehow reaches across space and changes the state of the second particle, right now, faster than any signal could possibly travel. Einstein calls this spooky action at a distance. He means it as an insult. The paper's conclusion is that quantum mechanics must be incomplete. There must be hidden variables, some deeper level of reality that determines the outcomes of measurements before they happen. The particles must carry secret instruction sets, even if we cannot see them. The correlations must be pre-established, baked into the system at the moment of interaction, not conjured out of nothing at the moment of measurement. Because the alternative is madness. The alternative is that the universe does not have a definite state until we look at it. The alternative is that reality is not real. Bohr responds almost immediately. His reply is dense, obscure, famous for being almost impossible to understand. But his central claim is simple. Einstein has misunderstood the situation. The two particles, once they interact, are no longer separate systems. They are one system, even if the parts are far apart. The measurement on one particle does not send a signal to the other. It reveals a correlation that was there all along, not a correlation of definite pre-existing values, but a correlation of possibilities, a relationship that only becomes definite when a measurement is made. The debate goes on for years. Einstein and Bohr argue in letters, at conferences, in the quiet rooms of physics institutes. Neither convinces the other. Einstein dies in 1955 still believing that quantum mechanics is incomplete, still waiting for the hidden variables to be discovered. Bohr dies in 1962 having defended the Copenhagen interpretation to the end, insisting that the moonlight question is simply not well posed, that asking whether the moon exists when nobody looks is asking a question without meaning. For 3 decades, most physicists side with Bohr. The hidden variable idea seems old-fashioned, even cranky. Quantum mechanics works. The predictions match the experiments. Why worry about what the particles are doing when no one is watching? The question is metaphysics, not physics. The sensible thing is to shut up and calculate. And then, in 1964, a young physicist at CERN, a shy Irishman named John Stuart Bell, changes everything. Bell is not famous in 1964. He works at the European Particle Physics Laboratory in Geneva, but his day job is accelerator design, not foundations of physics. The foundations work is something he does on the side in the evenings when he can steal time from his official duties. He has been thinking about the Einstein-Podolsky-Rosen argument for years. He has been wondering whether there is some way to test it, some way to turn the philosophical debate into an actual experiment, and he finds one. Bell's insight is deceptively simple. Suppose Einstein is right. Suppose there are hidden variables, secret instruction sets that the particles carry, undetectable by us, that determine how they will respond to measurements. If so, then the correlations between the two particles, no matter how strong, must obey certain limits. They must satisfy certain mathematical inequalities. The inequalities are not complicated. Any theory that respects local realism, any theory in which particles have definite properties before measurement and cannot influence each other faster than light, must satisfy them. But quantum mechanics predicts that the inequalities can be violated. Bell writes a short paper. It is published in an obscure journal, Physics Physique Physica, and almost no one notices. The paper proves a theorem, now called Bell's theorem, that draws a sharp line in the sand. On one side, local hidden variables, Einstein's dream, the moon existing whether or not anyone looks. On the other side, quantum mechanics, Bohr's vision, a universe whose properties are not fixed until they are observed. The two sides make different predictions. The predictions can be distinguished by experiment. For the first time in history, there is a way to test whether reality is real. The first serious attempt comes in 1972. John Clauser, a young experimentalist at Berkeley, builds an apparatus to create pairs of entangled photons, particles of light whose polarizations are correlated in exactly the way Einstein described. He sends the photons in opposite directions, measures their polarizations at various angles, and counts the correlations. The result? Quantum mechanics wins. The Bell inequalities are violated. The predictions of local hidden variables are wrong. But there are problems. The experiment has loopholes, technical imperfections that a sufficiently clever skeptic could exploit. Maybe the photons are communicating somehow, through some unknown mechanism. Maybe the detectors are biased, missing some of the photons in a way that skews the statistics. Maybe the experimenters are subconsciously choosing their measurement settings in a way that correlates with the hidden variables. Each loophole seems absurd, but each is technically possible, and as long as it is possible, the result is not airtight. Over the next 4 decades, experimenters closed the loopholes one by one. In 1982, Alain Aspect in Paris builds a faster apparatus, switching the measurement settings after the photons have already left the source. This closes the communication loophole. There is no time for a signal to travel between the particles. In 1998, a team in Geneva sends entangled photons through fibre optic cables to detectors in two villages 11 kilometres apart. The Bell inequalities are still violated. The effect does not diminish with distance. In 2015, the Delft experiment, the one led by Ronald Hansen in the Netherlands, closes nearly all the remaining loopholes simultaneously. The measurement settings are chosen by random number generators. The detectors are efficient enough to rule out bias. The particles are separated by more than a kilometre, and the measurements are made so quickly that no signal, even travelling at the speed of light, could carry information between them. The result is the same. Quantum mechanics wins. The Bell inequalities are violated by exactly the amount the theory predicts. Let that settle for a moment. What this means is that one of two things must be true. Either the particles are communicating faster than light, which would violate everything we know about relativity, everything we know about causality, everything we know about how information travels through the universe, or the particles did not have definite properties before they were measured. Almost all physicists choose the second option, not because it is comfortable, because it is the only one that does not break everything else. And this means, in turn, that the question Einstein asked, whether the moon is there when nobody looks, is no longer a joke. It is no longer a philosophical game. It is an open scientific question, one that the evidence so far answers in a way that Einstein would have found horrifying. The moon is made of atoms. The atoms do not have definite positions until they are measured. The moon, therefore, does not have a definite position, does not have a definite state, until something measures it. But wait, you say. The moon is always being measured. Light from the sun is bouncing off it. Particles from the solar wind are striking it. Cosmic rays are passing through it. The moon is never isolated, never free from interaction with the rest of the universe. Surely those interactions are enough to keep the moon solid, to keep it real, to prevent it from dissolving into a quantum blur. You are right. This is, in fact, the best answer physics has to offer. The moon stays classical, stays definite, stays solid, stays real, because it is constantly entangled with its environment. Every photon that bounces off the lunar surface carries away a tiny bit of information about where the moon is. Every interaction spreads the moon's state out into the universe, making it impossible to observe the quantum superpositions that would otherwise be present. This process is called decoherence, and it is very efficient. For an object the size of the moon, decoherence happens in a time so short that no experiment could ever measure it. The moon's position is, for all practical purposes, always definite. But notice what this answer does not say. It does not say that the moon has a definite position in some fundamental, observer-independent sense. It says that the moon appears definite to us because we are part of the same entangled web. It says that the moon and the photons and the cosmic rays and our eyes and our brains are all woven together in a vast quantum tapestry, and within that tapestry things look solid. But the tapestry itself, the universe as a whole, is still, in some sense, a superposition. Still, in some sense, not definite until what? That is the measurement problem. That is the question that no one has answered. Because if you follow the logic carefully, you realize that decoherence does not solve the puzzle, it just moves it around. Decoherence explains why the moon looks definite to us, but it does not explain why any outcome happens at all. It does not explain why, when you open the box, you see a live cat or a dead cat, rather than a superposition of both. It does not explain why the universe selects one branch of the wave function and not another. It does not explain, and this is the hard part, how measurement works. In the equations of quantum mechanics, there is no special role for measurement. There is no term that says collapse the wave function when a physicist looks at the apparatus. The equations are smooth, continuous, deterministic. The same equations that govern atoms govern laboratories. The same equations that govern laboratories govern experimenters. The same equations that govern experimenters govern the entire universe. If you trust the equations all the way up, you arrive at a strange conclusion. Every possible outcome of every measurement happens. The wave function never collapses. It just keeps branching endlessly into a vast tree of parallel histories. This is the many worlds interpretation. It is not fringe physics. It is the interpretation that the equations themselves seem to prefer if you refuse to add collapse by hand. And it says something remarkable. The moon is always there, in every branch, but there are also branches where the moon is not there, branches where the moon is somewhere else, branches where you measured a different thing, and the universe forked in a different direction. You just happen to be in this branch, seeing this moon, because this is the branch your observations have placed you in. Is that comforting? Is that troubling? I do not know. Neither do the physicists. The quiet testing continues. In Vienna, a team led by Anton Zeilinger has spent 2 decades pushing the limits of quantum superposition. They have demonstrated interference, the signature of quantum behavior, in molecules with hundreds of atoms, in organic molecules heavier than anything that should behave like a wave. They are working their way up, gram by gram, toward the macroscopic world. Their explicit goal is to find where quantum mechanics breaks down, to find the size at which objects stop being blurry and start being solid. So far, they have not found it. Every molecule they test behaves exactly as quantum mechanics predicts. The boundary, if it exists, keeps retreating. In California and Italy and China, physicists are building more elaborate Bell tests, using signals from distant quasars to choose the measurement settings, signals that left their sources billions of years ago, before the Earth existed, before any local hidden variable theory could have prearranged the results. They are closing the last, most paranoid loophole, the possibility that the entire experiment, including the experimenters themselves, is somehow correlated with the hidden variables at the moment of the Big Bang. The results so far are the same. The Bell inequalities are still violated. Quantum mechanics still wins. The moon question remains open, and the answer it suggests is still not the one Einstein wanted. Let me put that in perspective. We are living in a moment when the most fundamental question about the nature of reality, whether objects exist when no one is looking at them, is not a matter of philosophical speculation but of experimental investigation. We are living in a moment when the best minds in physics are seriously, carefully, painstakingly testing whether the universe has definite properties, or whether it is, at its core, a vast quantum blur that only resolves into solidity when something, somewhere, looks. And the tests keep coming back with the same answer. The blur is real. The definiteness is an illusion. The moon is there when you look at it, but the equations do not quite guarantee it was there a moment before. There is a story, almost certainly apocryphal but too good not to tell, about a conversation between Einstein and Niels Bohr at one of the great physics conferences of the early 20th century. Einstein, the story goes, is frustrated. He has been making arguments against quantum mechanics all week, and Bohr has been patiently refuting them. Finally, Einstein plays what he thinks is his trump card. He gestures out the window at the night sky. "Do you really believe," he asks, "that the moon is not there when nobody looks at it?" Bohr pauses. He considers the question carefully, and then he asks in reply, "Can you prove that it is?" The question hangs in the air. Einstein, for once, has no answer, because the truth is you cannot prove it. You cannot design an experiment that shows the moon existing when no one is observing it, because the experiment by definition would be an observation. The question, is the moon there when nobody looks, is, in a certain technical sense, unanswerable. It sits outside the reach of science, in the same uncomfortable zone as questions about consciousness, about free will, about what it is like to be something else. But here is what physics can do. Physics can test the consequences. Physics can ask whether the properties that appear when you do look are pre-established or newly minted. Physics can design experiments that distinguish between a universe with hidden instruction sets and a universe without them. Physics can, in other words, creep up on the moon question from an angle, testing its implications even if it cannot test the question directly. And when physics does that, when it runs the Bell tests, when it closes the loopholes, when it sends entangled photons through kilometers of optical fiber and measures their correlations to 14 decimal places, the answer is always the same. The instruction sets are not there. The properties are not pre-established. The outcomes are not decided in advance. The moon, as far as the equations are concerned, does not have a definite position until something measures it. Think about what that means for a moment. Not the physics. You have heard the physics. Think about what it means for you, lying in the dark looking up at a glowing screen, reading about a rock in the sky. You have always assumed, without even thinking about it, that the world is simply there, that the chair beneath you exists whether or not you sit in it, that the walls of the room exist whether or not you touch them, that the universe, in its vast and patient way, goes on being the universe even when you are not paying attention. That assumption is called realism. It is so intuitive, so automatic, so deeply woven into the way you think, that you probably never noticed you were making it. It is the assumption that there is an external world, independent of your perceptions prior to your observations, out there waiting to be discovered rather than created. Quantum mechanics does not quite destroy that assumption, but it bends it. It says that, at the deepest level, the world does not have definite properties, only probabilities, correlations, relationships. It says that what you perceive as solid reality is a surface phenomenon, an emergent pattern, a way of talking about what happens when the probabilities resolve into actualities. It says that the line between the observer and the observed is not as clear as you thought, that you are not a camera passively recording a pre-existing scene, but an active participant in the unfolding of the world. This is not mysticism. The physicists who believe this are not saying that the universe is imaginary, or that consciousness creates reality, or that you can manifest your desires by thinking positive thoughts. They are saying something much stranger and much more precise, that the mathematical structure of the world, at its most fundamental level, does not contain the solidity you expect. The solidity is real in the sense that you experience it. The solidity is not fundamental in the sense that it is built into the equations. The solidity, the definiteness, the there-ness, the thisness, emerges from quantum interactions, from entanglement, from the ceaseless web of measurements that the universe performs on itself. And the moon, in this picture, is just a particularly striking example. A giant rock in the sky, seemingly as solid as anything in existence, serving as a test case for the deepest question in physics. Is it there when no one is watching? The experiments say, not in the way you thought, not in the way Einstein wanted, not in the way common sense demands. The experiments say something else is going on, something stranger, something we are still learning to articulate. Outside your window, if the clouds have cleared, the moon is rising, the same face it has shown to every human generation. The same grey seas, the same white highlands, the same pattern of craters that you learned to recognise as a child. It looks solid, it looks real, it looks like it has been there forever and will be there forevermore. But behind that appearance, behind the photons streaming toward your eyes, behind the reflected sunlight and the tidal pull and the gravitational embrace of the Earth, there is a question that physics cannot yet answer. What is the moon doing right now, when the light has not yet arrived? What was the moon doing a moment ago before your observation resolved its position? What's the moon doing in the stretches of space where no eye, no detector, no interaction of any kind reaches? The equations say the moon is in a superposition. The equations say the moon has many positions weighted by probabilities until something pins it down. The equations say there is no there until there is a measurement to create it. Most physicists do not think the equations mean this literally. Most physicists think there is something missing, some principle of decoherence or selection or consciousness, or physics we have not yet discovered that rescues the moon from limbo. But they cannot point to that something. They cannot write it in an equation. They cannot test it in an experiment. All they can do is run the Bell tests and close the loopholes and confirm again and again that the universe does not have hidden instruction sets, that the properties of objects are not fixed before measurement, that the weirdness is real. And so the question remains. The moon hangs in the sky, silent and silver, offering no answers. It has been circling the Earth for 4.5 billion years. It has seen the oceans form and the continents drift, and life crawl out of the water onto dry land. It has watched every civilization rise and fall, every empire flicker and fade, every human being live and die and return to dust. It looks like the most solid thing in the universe. But the physicists are quietly testing. The experiments are still running, and the results so far suggest that the moon is not quite what it seems. Let that settle for a moment. The night is long and there is much more to tell. The story of how we arrived at this strange place, this quiet crisis at the foundations of physics, begins not with the moon, but with light. and not with any grand cosmic light, but with the humblest kind. The glow of a heated filament, the soft radiance of a lamp, the sort of light that fills a room and lets you read a book. In the early years of the 20th century, physicists were confident they understood light. It was a wave. It rippled through space like sound ripples through air, like water ripples across a pond. James Clerk Maxwell had written the equations 60 years earlier, and they were beautiful, and they worked. Light was an electromagnetic wave, a disturbance in invisible fields, oscillating at frequencies that determined its colour. Red light oscillated slowly, blue light oscillated quickly. The equations predicted how light would bend through a prism, how it would diffract around an edge, how it would interfere with itself to produce the shimmering patterns you see on a soap bubble. Everything fit. Everything made sense. And then, in 1900, a German physicist named Max Planck ruined it. Planck was not trying to revolutionize physics. He was trying to solve a very specific, very technical problem involving the light emitted by hot objects. When you heat a piece of metal, it glows. First a dull red, then a brighter orange, then yellow, then white if you get it hot enough. The question was, how much light does it emit at each colour? The classical equations, the beautiful Maxwell equations, the established wave theory, gave an answer, and the answer was wrong. Not slightly wrong, catastrophically wrong. The classical equations predicted that a hot object should emit infinite energy at high frequencies. Infinite. This was obviously absurd. The universe was not exploding in a blaze of ultraviolet light every time you heated a poker. The equations that worked so perfectly for other phenomena were failing completely when pushed to their limits. Planck found a fix. But the fix required him to do something that seemed at the time like a mathematical trick, a temporary kludge, a placeholder, until someone found the real answer. He had to assume that light could only be emitted or absorbed in discrete chunks, not continuous streams, not smooth waves, packets, bundles, quanta. And the energy of each quantum was proportional to its frequency, multiplied by a tiny number that Planck had to calculate from the experimental data. That number, Planck's constant, is one of the fundamental constants of nature. It is incredibly small, about 6.6 times 10 to the minus 34 joule seconds. A decimal point, then 33 zeros, then a 6. So small that you would never notice it in everyday life. So small that light behaves like a continuous wave for all practical purposes at human scales. But it is not zero. And because it is not zero, the universe is quantized. The universe comes in packets. The universe at its deepest level is not smooth. Planck did not quite believe his own solution. He spent years trying to find a way to make the quantum go away, to recover the smooth classical picture. He could not. No one could. And 5 years later, a young patent clerk in Switzerland named Albert Einstein showed that the quantum was not just a mathematical trick. It was real. Light actually came in particles, photons, discrete bundles of energy that could be counted one by one. Einstein proved this by explaining the photoelectric effect, the strange phenomenon where light shining on a metal surface can knock electrons loose, but only if the light is above a certain frequency, regardless of how bright it is. If light were a pure wave, brightness should matter. More brightness, more energy, more electrons knocked free. But that is not what happens. What matters is the frequency. Red light, no matter how bright, cannot knock electrons off certain metals. Ultraviolet light, even dim ultraviolet light, can. Einstein explained this by proposing that light is absorbed one photon at a time. Each photon carries a fixed amount of energy determined by its frequency. If that energy is too low, the electron stays put. If it is high enough, the electron escapes. One photon, one electron. Discrete, quantized, real. Einstein received the Nobel Prize for this work, not for relativity, the photoelectric effect, the proof that light comes in particles, and yet, and this is where the strangeness begins, light also comes in waves. The interference patterns, the diffraction, the soap bubble shimmer, those are wave phenomena. They cannot be explained by particles bouncing off each other like tiny billiard balls. Light is both. Light is neither. Light is something else entirely, something that has no analogue in the everyday world of stones and water and sound. This is wave-particle duality. and it was the first great crack in the classical picture of reality, the first hint that the universe does not work the way human intuition expects, the first whisper of the strangeness to come. Let that settle for a moment. By the 1920s, the cracks had widened into chasms. Physicists were discovering that it was not just light that behaved this way. Electrons behaved this way too, and atoms, and everything else, down to the smallest scales they could probe. The French physicist Louis de Broglie proposed in 1924 that every particle has a wavelength just like light. Not metaphorically, actually. The wavelength is equal to Planck's constant divided by the particle's momentum. For large, slow objects, a baseball, a car, a human being, the wavelength is so unimaginably tiny that it has no measurable effect. The wavelength of a walking human is roughly 10 to the minus 35 meters. That is a trillion times smaller than an atom. For all practical purposes, you are a particle. Your wave nature is unmeasurable. But for electrons, the story is different. Electrons are light. Electrons move fast. The wavelength of an electron in a typical experiment is comparable to the spacing between atoms in a crystal. And in 1927, two American physicists, Clinton Davison and Lester Germer, proved that electrons behave like waves. They fired electrons at a nickel crystal and observed an interference pattern. Not the scattering you would expect from tiny bullets bouncing off atoms. An interference pattern. The kind of pattern that only waves can make. The electrons were going through the crystal, and they were interfering with themselves like ripples crossing on a pond. This was impossible. This was absurd. Electrons are particles. You can count them. You can trap them. You can fire them one by one from an electron gun. And yet, when you send them through a crystal, or through a pair of slits, they behave like waves. They spread out, they interfere, they create patterns that make no sense if you think of them as tiny balls. The Austrian physicist Erwin Schrödinger responded to this chaos by writing down an equation. The Schrödinger equation. It is in some ways the central equation of quantum mechanics. It describes how the wave function of a quantum system evolves over time. And the wave function, this is the crucial point, is not a description of where a particle is. It is a description of where a particle might be. It is a description of probabilities. The wave function gives you a number, actually a complex number, a number with a real part and an imaginary part, for every possible position in space. The square of that number gives you the probability of finding the particle at that position, if you choose to look. Before you look, the particle does not have a position. Not in the classical sense, not in the sense that there is a fact of the matter about where it is. The wave function is spread out. The particle is in some sense everywhere at once. Everywhere the wave function is non-zero, weighted by those probabilities. And the wave function evolves, it spreads, it flows through space according to the Schrödinger equation, like water flowing through a pipe, but a very strange kind of water, a water made of possibilities rather than substance. Then you look, then you make a measurement, and something happens. Something that Schrödinger's equation does not describe, something that the mathematics cannot explain. The wave function collapses. All those spread out probabilities snap into a single outcome. The electron which was everywhere is suddenly somewhere, a definite position, a definite result. You find it here, not there. And afterward, the wave function starts spreading again from that point, evolving according to the equation, until the next measurement comes along. This is the measurement problem. This is the crack at the heart of quantum mechanics that has never been sealed. The Schrödinger equation describes the evolution of possibilities. But when you make a measurement, possibilities become actualities. One outcome is selected from the many. And nothing in the mathematics tells you why that outcome was chosen, or how or what caused the other outcomes to disappear. The mathematics just says, before measurement, superposition, after measurement, single result. The mathematics does not explain the transition. The mathematics does not contain the mechanism. The mathematics simply describes two different regimes, the smooth evolution of possibilities and the sudden snap into actuality, and leaves the connection between them as a mystery. Einstein hated this. Einstein spent the last 3 decades of his life fighting against this picture, searching for an alternative, insisting that there must be something deeper, something hidden, something that would restore the classical dream of a universe with definite properties independent of observation. He famously said that he could not believe that God plays dice with the universe. He even more famously asked whether the moon was still there when no one was looking at it. He posed thought experiments designed to expose the absurdity of the quantum view, to show that it led to contradictions or impossibilities, to force his colleagues to admit that something was missing. The most famous of these thought experiments is the Einstein-Podolsky-Rosen paradox, published in 1935. It is a dense argument, technical in places, but its core can be expressed simply. Quantum mechanics says that certain properties of particles are not fixed until you measure them. Einstein asked, what if you have two particles that are correlated? What if you create a pair of particles that are entangled, linked together in such a way that measuring one tells you something about the other? And what if you separate these particles by a great distance before you measure them? Here is the scenario. You create two particles in an entangled state. You send one to Alice, on Earth. You send the other to Bob, on the Moon. The particles are correlated. If Alice measures her particle and finds it spinning clockwise, quantum mechanics predicts that Bob's particle will be spinning counterclockwise every time without fail. But according to the standard quantum view, neither particle has a definite spin direction before measurement. The spin is not fixed, it is in superposition. It becomes definite only when Alice makes her measurement. But now here is the puzzle. Alice measures her particle. She finds it spinning clockwise. Instantly, according to quantum mechanics, Bob's particle becomes spinning counterclockwise. Not after a signal has time to travel from Earth to the Moon. Instantly. The wave function that described both particles collapses everywhere all at once. Einstein said, "This cannot be right. Nothing can travel faster than light." This is one of the foundational principles of his own theory of relativity. If measuring Alice's particle instantaneously affects Bob's particle, then something is travelling faster than light. Some influence, some signal, some spooky action at a distance. Einstein's own phrase, spoken in German as spukhaft Fernwirkung, is reaching across space and changing the state of Bob's particle. And that, Einstein said, is impossible. Therefore, the quantum description must be incomplete. There must be hidden variables. There must be some information carried by each particle from the moment of their creation that determines how they will behave when measured. The particles knew all along how they would spin. The correlation was built in from the start. Quantum mechanics, in failing to describe these hidden variables, is simply ignorant of the full picture. Reality is still definite. Reality is still local. Quantum mechanics just hasn't found the complete description yet. This was Einstein's hope. This was his lifeline back to the classical picture. Hidden variables, instruction sets, a layer of reality beneath the quantum description that would restore definiteness, restore locality, restore sanity. And for nearly 30 years, this hope seemed reasonable, maybe even likely. Many physicists agreed with Einstein. The quantum formalism was just a tool, a calculational recipe, a way of predicting probabilities without revealing the deeper machinery. Someday, someone would find the hidden variables. Someday, physics would wake up from this strange dream. Then, in 1964, an Irish physicist named John Stuart Bell destroyed that hope. Bell was working at CERN, the European Particle Physics Laboratory in Geneva. He was quiet, careful, precise. He had a gentle manner and a devastating intellect, and he had spent years thinking about the Einstein-Podolsky-Rosen paradox, about hidden variables, about what quantum mechanics really implied. What Bell discovered is this: if hidden variables exist, they must obey certain constraints. They must produce correlations that stay within certain bounds. He derived these bounds mathematically, expressing them as an inequality, a relationship between measurable quantities that any hidden variable theory must satisfy. This is Bell's inequality. And then he showed that quantum mechanics predicts violations of this inequality. Quantum mechanics predicts correlations that are stronger than any hidden variable theory can produce. Not by a little, by a measurable amount. This was not philosophy. This was not interpretation. This was a testable prediction. You could build an experiment. You could create entangled particles. You could measure them in various ways. You could calculate the correlations, and you could compare those correlations to Bell's inequality. If the correlations exceeded the Bell limit, then hidden variables were ruled out. If the correlations stayed within the limit, then Einstein was right and quantum mechanics was incomplete. The experiments were run. first by John Clauser in the 1970s, then by Alain Aspect in France in the 1980s, then by dozens of other teams around the world with increasingly sophisticated equipment, closing loophole after loophole. The results were always the same. The correlations exceeded the Bell limit. Quantum mechanics was right. Hidden variables, at least the local kind that Einstein had hoped for, were wrong. Let me say that again because it is worth sitting with. The experiments ruled out the idea that particles carry hidden instruction sets. The experiments ruled out the idea that the properties of particles are fixed before measurement. The experiments showed that, whatever is happening in quantum mechanics, it is not simply that we are ignorant of deeper information. The weirdness is not due to incomplete knowledge. The weirdness is built into the fabric of reality. Rest with that for a moment. This does not mean that reality is subjective. It does not mean that consciousness creates particles. It does not mean that you can change the world by wishing hard enough. What it means is subtler, stranger, and more difficult to articulate. It means that the universe does not have the structure we intuitively expect. It means that objects do not have definite properties, independent of how they are observed. It means that the correlations between distant particles are stronger than any classical mechanism can explain. It means that something, we do not know what, is connecting the outcomes of measurements in ways that cannot be accounted for by signals travelling through space. Einstein called it spooky action at a distance, and the spookiness has only deepened with time. The experiments have grown more precise, the distances have grown larger, the loopholes have grown smaller, and still the quantum correlations hold. Still the Bell inequality is violated. Still the universe refuses to fit into the classical box. The moon, in this context, is merely a thought experiment, a rhetorical device, a way of making the abstraction vivid. Einstein asked about the moon because it was the most absurd example he could think of. Of course the moon has a definite position. Of course the moon exists when you're not looking at it. The suggestion that it might not is ridiculous, preposterous, obviously wrong. But the equations do not say the moon has a definite position. The equations say the moon has a wave function. The equations say that wave function is a superposition of many possible positions, weighted by probabilities until something, decoherence, measurement, interaction with the environment, selects one. The equations treat the moon exactly like they treat an electron, just with different numbers plugged in. The mass is larger. The Planck constant is the same. The wavelength of the moon is absurdly, unmeasurably tiny. But the mathematical structure is identical. If you take quantum mechanics seriously, if you believe the equations are not just calculational tools but descriptions of reality, then you are forced to ask, what is the moon doing when no one is measuring it? Most physicists answer this question by invoking decoherence. The moon is not isolated. The moon is constantly interacting with the Earth's gravitational field, with the light of the sun, with cosmic rays, with the microwave background radiation that fills all of space. These interactions entangle the moon with its environment. They spread the moon's quantum information into the surrounding world, diluting the superposition, making it impossible, for all practical purposes, to observe quantum effects at the scale of the moon. The moon behaves classically because it is too big, too warm, too connected to hide its quantum weirdness. The weirdness is there, in principle, but it is undetectable. It has leaked out into the environment. It has become, for practical purposes, invisible. This is a reasonable answer. It is probably the correct answer as far as it goes. But notice what it does not do. It does not explain the measurement problem. It does not explain why the wave function appears to collapse. It does not give the moon a definite position in some absolute sense. It just explains why we cannot detect the moon's quantum indefiniteness. The indefiniteness is hidden, not resolved. The question remains, lurking beneath the practical answer, what is the moon doing, really? When the decoherence has done its work and the classicality has emerged, and all the experiments give definite results, is there a fact of the matter? Or is the definiteness itself an illusion, a statistical summary of quantum correlations, a pointer reading that does not correspond to any underlying reality? This is where the interpretations begin, and this is where physicists start to disagree, not about the experiments, not about the mathematics, but about what it all means. Some say the wave function is real. This is the view associated with Hugh Everett and the many worlds interpretation. In this picture, the wave function never collapses. Every outcome of every quantum measurement actually occurs. The universe splits continuously into branches, each branch containing a version of you that experienced a different result. When you measure an electron and find it here, there is another branch of reality where you measured it and found it there. Both outcomes are real. Both versions of you are real. The apparent collapse is just what it feels like from inside one branch, unaware of the others. Some say the wave function is epistemic, a description of knowledge rather than reality. In this view, particles do have definite states, but we cannot access them directly. The wave function represents our uncertainty, our predictions, our best guesses, not the actual configuration of the world. This view has trouble with Bell's theorem because Bell showed that local hidden variables cannot reproduce the quantum predictions. But some versions of this view accept non-locality. Some accept that the hidden variables are strange, non-classical, connected in ways that defy ordinary causation. Some say the wave function is incomplete, that there is some additional process, perhaps involving consciousness, perhaps involving a new physical law, perhaps involving random collapses at certain scales, that converts possibilities into actualities. These are the objective collapse theories, the GRW model, the Penrose hypothesis, the idea that quantum mechanics as we know it is only an approximation to a deeper theory that will eventually explain where the definiteness comes from. And some say we should not ask. Some say the question is meaningless, that the wave function is just a tool for prediction, that physics describes what we can measure and nothing more, that asking what the moon is doing when no one is watching is like asking what is north of the North Pole. These are the instrumentalists, the pragmatists, the physicists who prefer to calculate and leave the philosophy to others. None of these interpretations changes the predictions. None of them affects the outcomes of experiments. None of them tells you whether the moon has a definite position right now. They are all consistent with the mathematics. They are all consistent with the data. And physicists, lacking any way to distinguish between them experimentally, have been arguing about them for nearly a century. The arguments continue today. The experiments continue today. And the moon continues to hang in the sky, silent and silver, offering no resolution. It has been there for 4.5 billion years. It will be there long after these arguments are settled, if they are ever settled. It is the same moon that Einstein looked at when he asked his famous question. The same moon that Bohr looked at when he insisted the question was ill-posed. The same moon that you are looking at now, if you have paused to glance out the window, if the clouds have parted, if the night is clear. The physicists are still testing. The experiments are still running. And somewhere in the gap between the mathematics and the meaning, the deepest question in physics remains open. What is reality made of? What is the universe doing when no one is watching? And is the moon, that ancient, patient, silent companion, really there when you look away? The night is long, there is more to tell, and the strangest chapters are still ahead. The strangest chapters begin not in a physics laboratory, but in a basement in Maryland in 1972, with a man named John Clauser and a machine he built mostly by hand. Clauser was a young physicist then, freshly minted, restless and stubborn in the way that good experimentalists often are. He had read Bell's paper, he had understood what it implied, and he had done something that almost no one else in physics was willing to do at the time. He had decided to test it. You have to understand how unusual this was. In 1972, quantum mechanics was already the most successful theory in the history of science. It had predicted the energy levels of atoms to 12 decimal places. It had explained the behavior of semiconductors and superconductors. It had given physicists lasers, transistors, the entire foundation of modern electronics. And yet, hidden inside its mathematics, there was this strange, troubling implication that almost no one wanted to examine too closely. The implication was entanglement. The implication was that two particles, once connected, would remain connected across any distance, responding to each other instantly, as if space itself did not exist between them. Einstein had called it spooky action at a distance. Bohr had insisted it was just the way the mathematics worked, nothing more. And for decades, physicists had agreed mostly to leave the question alone. Bell changed that. Bell showed that if you took Einstein's objections seriously, if you assumed that particles had definite properties before measurement and that no influence could travel faster than light, then the correlations between entangled particles would obey a certain mathematical limit. This limit is now called Bell's inequality. and Bell showed that quantum mechanics predicts violations of this limit. The correlation should be stronger than any local hidden variable theory could explain. Much stronger. The mathematics was clear. The implication was staggering. If quantum mechanics was right, then either particles did not have definite properties before measurement, or information was travelling between them faster than light, or both. There was no comfortable middle ground. There was no way to preserve the classical picture of the world, and yet for years almost no one tested it. The experiment seemed too difficult. The implications seemed too strange. The physics community had made its peace with the Copenhagen interpretation, with the idea that quantum mechanics was complete as a predictive tool, and that deeper questions about reality were best left to philosophers. John Clauser did not agree. He built his apparatus in the basement of the University of California, Berkeley. It was a crude machine by modern standards, a tangle of optics and photomultipliers and vacuum pumps. It produced pairs of photons, entangled in their polarization, and sent them to two separate detectors. At each detector, a polarizer was set to a random angle. The photons arrived, the polarizers measured, the results were recorded. The experiment ran for months. The data accumulated click by click, photon by photon in the silent basement. And when Clauser finally analysed it, he found what Bell had predicted. The correlations violated the inequality. The photons were more correlated than any local theory could explain. They were responding to each other across the distance of the lab instantly, as if no space separated them at all. Clauser published his results. The physics community noticed, and then, for the most part, the physics community looked away. It is strange, in retrospect, how little attention the result received. Here was experimental proof that the world did not work the way classical physics said it worked. Here was evidence that reality, at its deepest level, was woven together in ways that defied ordinary causation. And yet, the response was muted. The papers were cited, the result was acknowledged, but the implications were not pursued. The physics community returned to its calculations, to its accelerators, to the practical business of building better semiconductors and more powerful lasers. Clauser himself was frustrated by this. He had expected the result to transform physics. He had expected it to force a reckoning with the foundations of quantum mechanics. Instead, it became a footnote, a curiosity, a result that everyone knew about and no one wanted to discuss. Decades passed. The experiments were repeated, refined, improved. Alain Aspect, working in Paris in the early 1980s, built a more sophisticated version of Clauser's apparatus. His detectors could switch their settings after the photons were already in flight, closing one of the loopholes that skeptics had pointed to. The results were the same. The correlations violated Bell's inequality. The world was not local. More experiments followed. Different particles, different setups, different labs around the world. The results always agreed. The correlations were always too strong. The violations were always there. And still, the physics community did not quite know what to do with it. Let that settle for a moment. Picture the situation. Here are experiments, dozens of them, hundreds of them, conducted by some of the most careful experimentalists in the world, all pointing to the same conclusion. The universe is not locally real. Particles do not have definite properties before measurement, or if they do, those properties are connected across space in ways that violate ordinary causation. Either possibility is revolutionary. Either possibility should have rewritten the textbooks, and yet, for decades, the textbooks barely mentioned it. The reason is partly sociological. Physics, like any human enterprise, has its fashions and its taboos. In the mid-20th century, questioning the foundations of quantum mechanics was considered slightly disreputable. The Copenhagen interpretation had won. The practical applications were piling up. There was no professional reward for asking what it all meant. The reason is also partly philosophical. The Bell violations did not tell physicists which interpretation was correct. They ruled out local hidden variables, at least in their simplest form. But they did not distinguish between many worlds and objective collapse, between pilot waves and instrumentalism. The experiments narrowed the options. They did not settle the question. And the reason is also partly psychological. The implications are uncomfortable. They suggest that the world is not what we think it is. They suggest that the solid, definite, observer-independent reality that we experience in everyday life is, at some level, an illusion. Not everyone wants to confront that. Not everyone is prepared to follow the mathematics wherever it leads. But some physicists did follow it. Some physicists are still following it today. This is where the story turns quieter and stranger and begins to approach the moon. In 2015, 3 separate experiments conducted on 3 separate continents closed the last major loopholes in the Bell tests. These were loophole-free Bell tests, designed to eliminate every conceivable objection. The detectors were efficient enough to catch nearly every photon. The settings were chosen by quantum random number generators, unpredictable by any local mechanism. The particles were separated by distances large enough that no signal, travelling at the speed of light, could have passed between them during the measurement. The results were unambiguous. The correlations violated Bell's inequality. Again, still, always. The universe is not locally real. This phrase, not locally real, has a precise technical meaning. It means that either locality is false, and influences can travel faster than light, or realism is false, and particles do not have definite properties before measurement, or both. The experiments cannot distinguish between these options. They can only rule out the comfortable classical picture where particles have definite states and no spooky action occurs. The 2015 experiments were published in Nature and Physical Review letters. They were reported in newspapers around the world, and this time, the physics community did pay attention. The researchers who conducted them, Clauser, Aspect, and Anton Zeilinger, received the Nobel Prize in Physics in 2022. The citation specifically mentioned their work on Bell inequalities and entanglement, and yet even now the deeper question remains open. What does it mean? What is the universe actually doing? What is the moon doing when no one is looking? The Nobel Prize did not answer these questions. The experiments did not answer them. The mathematics, perfect and consistent, does not answer them. The answer depends on which interpretation you choose, and physicists to this day cannot agree. Some of them have decided to stop arguing and start building. This is the chapter that the textbooks are only now beginning to write. It is the chapter where the philosophy meets the engineering, where the abstract debates about the nature of reality start to have practical consequences. And it begins with a simple idea, an idea so strange that it sounds like science fiction until you realize that experiments have already demonstrated it. The idea is this: if quantum mechanics is true, if particles really do not have definite states until measured, then it should be possible to use this fact. It should be possible to build devices that exploit superposition and entanglement to do things that no classical device can do. It should be possible to build a quantum computer. A quantum computer is not just a faster classical computer, it is something fundamentally different. A classical computer stores information in bits, each one a 0 or a 1, definite and unchanging until deliberately flipped. A quantum computer stores information in qubits, each one existing in a superposition of 0 and 1 simultaneously, both at once, neither fully until measurement forces a choice. When you have 2 qubits, they can be entangled, correlated in that strange quantum way that Bell's inequality tested. When you have many qubits, the number of simultaneous states grows exponentially. A quantum computer with just a few hundred qubits can represent more states than there are atoms in the observable universe. This is not a metaphor. This is not an exaggeration. This is the mathematics of quantum mechanics applied directly. And here is where the question of the moon becomes practical. A quantum computer only works if superposition is real, if particles genuinely exist in multiple states at once, if the wave function is not just a description of our ignorance, but a description of something in the world, if the moon, in some sense, really does not have a definite position until measured. If Einstein was right, if particles have definite states all along and we simply do not know them, then a quantum computer should not work. The supposed exponential speed-up comes from the superposition, from the ability to explore many possibilities at once. Without real superposition, there is nothing to exploit. The quantum computers being built today are testing this, not directly, not philosophically, but practically. They are asking, in effect, whether the mathematics of quantum mechanics describe something real. If the mathematics is just a predictive tool, a convenient fiction, then these devices should fail. They should not be able to do what quantum mechanics says they can do. So far they are doing it. The devices are still small, The largest quantum computers have a few hundred qubits, maybe 1,000. They are fragile, prone to errors, requiring temperatures colder than outer space to operate, but they are real. They are performing calculations. They are demonstrating in silicon and superconducting circuits. That superposition is not a philosopher's abstraction. It is a physical resource. And every time a quantum computer runs a calculation that a classical computer cannot, it is providing evidence, indirect but powerful, that the wave function is more than a mathematical convenience. The moon may not have a definite position, but the evidence is accumulating. Rest with that for a moment. Let it settle. The quietest revolution in physics is happening not in the arguments but in the machines. The debates about interpretation continue. The philosophers still disagree, but the engineers are building devices that only work if one side of the debate is correct. There is a test here, a real test, but it is not the kind of test that settles arguments in a single stroke. It is a test that unfolds over decades as the technology improves, as the devices grow larger and more capable, as the calculations become more sophisticated. It is a test that the universe is administering slowly and silently, while the physicists watch and wait. But there are other tests too, tests that approach the question more directly, tests that are, even now, running in laboratories around the world. Let me tell you about one of them. In Vienna, in a laboratory filled with lasers and mirrors and fiber optic cables, a team of physicists has been conducting an experiment that stretches back more than 2 decades. They have sent entangled photons across the city, through the open air from rooftop to rooftop. They have sent them through underground cables. They have sent them, in one memorable experiment, to a satellite in orbit and back. The distances are vast. The photons travel kilometers, sometimes hundreds of kilometers, before being measured, and every time the correlations are there. Every time the Bell inequality is violated, every time the universe refuses to be locally real. But the Vienna experiments are not just replications, they are explorations. They are pushing the boundaries, asking how far the entanglement can stretch, how long it can last, how robust it is against the noise and chaos of the real world. And they are asking another question too, a question that brings us back to the moon. The question is this: does quantum mechanics apply to large objects? The photons in these experiments are single particles, individual quanta of light. They are as small as physical objects can be. The rules of quantum mechanics were discovered for objects like this. No one doubts that photons can be in superposition, that electrons can be entangled, that atoms can exist in multiple places at once. But what about larger things? What about molecules? What about grains of sand? What about cats or moons or human beings? The mathematics of quantum mechanics makes no distinction. The Schrödinger equation applies to photons and to planets alike. There is nothing in the formalism that says superposition stops at a certain size. And yet, we do not see cats in superposition. We do not see moons blurred across the sky. We do not experience ourselves as existing in multiple states at once. This is the measurement problem wearing a different mask. This is the question of where quantum ends and classical begins. And this question, unlike the interpretive debates, is one that experiments might actually answer. The experiments are difficult. Larger objects are harder to isolate from their environment. They interact with air molecules, with photons of light, with the vibrations of the lab floor. These interactions cause decoherence, the leaking away of quantum behavior into the noise of the world. To see quantum effects in larger objects, you have to protect them from this noise. You have to cool them, shield them, suspend them in near-perfect isolation. But physicists are doing it. In laboratories around the world, researchers have placed larger and larger objects into quantum superposition. Molecules with hundreds of atoms, tiny mechanical oscillators, barely visible to the naked eye, microscopic drumheads, vibrating and not vibrating at the same time. Each experiment pushes the boundary a little further. Each experiment tests whether there is some size, some mass, some threshold where quantum mechanics breaks down and classical physics takes over. Each experiment is a probe into the edge of reality. So far, the boundary has not been found. Every object that has been carefully isolated and tested has obeyed quantum mechanics. The superpositions are fragile. They collapse quickly when the object interacts with its environment. But while they last, they are real. The mathematics describes them perfectly. This brings us to the moon. The moon is large. The moon is not isolated. The moon is bathed in sunlight and cosmic rays and the reflected glow of Earth. It interacts with trillions of particles every second. Any superposition it might have would decay almost instantly, collapsing into a definite state before any observer could notice. This is why, in practice, the moon always has a definite position. Not because quantum mechanics fails at large scales, but because the moon is so thoroughly entangled with its environment that no superposition survives. But here is the subtle point. Here is what the experiments are quietly revealing. The moon has a definite position because it has been measured, not by us, not by human observers, but by the environment, by the photons bouncing off its surface, by the gravitational influence of Earth and Sun, by the particles of solar wind streaming past. Measurement in quantum mechanics is not something that requires consciousness. It is not something that requires a human observer. It is any interaction that transfers information, any process that entangles a system with its surroundings. The moon is measured constantly. The moon is measured by everything. And this, perhaps, is the answer to Einstein's question. The moon does not need you to look at it. The universe is looking at it all the time. But this answer opens new questions. If measurement is just interaction, if observation is just entanglement, then what collapses the wave function? What determines which outcome occurs? What decides that the moon is here rather than there? The many worlds interpretation says nothing decides. All outcomes occur. The universe splits, and every possible position of the moon is realized somewhere, in some branch. You experience one branch because you're in it. The moon appears definite because you and the moon are in the same branch, entangled together by your shared history of interactions. The objective collapse theories say something does decide. Some physical process, perhaps involving gravity, perhaps involving mass, perhaps involving timescales we do not yet understand, causes the wave function to collapse spontaneously. The moon has a definite position because the collapse has already happened, long before any human looked. The pilot wave theories say the moon always had a definite position. The wave function guides it, like a field guiding a particle, but the position was always there, always real, always singular. The appearance of probability is just the appearance. The reality is deterministic underneath, and the instrumentalists say we should not ask. The question is meaningless. The moon is there when we measure it. What it does when we do not measure it is not a question physics can answer. These are the options. These are the stories physicists tell, and the experiments, powerful as they are, cannot yet choose between them. But they are trying. In the next generation of experiments, researchers plan to push further. They plan to test larger objects, heavier objects, objects approaching the threshold where some theories predict collapse should occur. They plan to test the interplay between gravity and quantum mechanics to see whether space-time itself plays a role in the transition from quantum to classical. They plan to send entangled particles across ever greater distances to satellites in deep space, to probes beyond the orbit of the moon. The moon itself may become a laboratory. Plans are being discussed quietly in conference rooms and grant proposals to conduct quantum experiments on the lunar surface. The vacuum is better there, the isolation is greater, the distances are vast enough to test ideas that cannot be tested on Earth. And somewhere in those experiments, in the click of a detector or the absence of a signal, the answer may be waiting. The night is still long. The moon is still hanging there, silver and silent, keeping its secrets. And the physicists, patient as always, are still watching, still measuring, still asking the question that Einstein asked nearly a century ago. Is the moon there when nobody looks? The question remains open. The tests continue. And the universe, vast and strange and endlessly surprising, offers no easy answers. Only more experiments, only more data, only the slow, careful, patient work of science, feeling its way toward the truth. The story is not finished. There is more to tell. And the quietest revolution is still unfolding, in basements and mountain tops and orbiting satellites, in the spaces between the mathematics and the meaning. The experiments that are coming will not look like anything you have seen before. Picture a laboratory not on Earth but suspended in the void, a metal cylinder tumbling slowly through the blackness between worlds. No air touches it. No vibration from a passing truck or a closing door reaches its instruments. The temperature outside is 3 degrees above absolute zero, and inside, in a chamber the size of a shoebox, a crystal smaller than a grain of sand floats in perfect isolation, held by nothing but light. This is the next frontier. This is where the question travels now. The crystal is not an atom. It is not a molecule. It is a genuine object, something you could see with the naked eye if the light were right. Something that weighs more than 1 trillion atoms bound together in a lattice of silicon and oxygen. And the researchers who designed this experiment want to do something that would have seemed impossible a generation ago. They want to put this crystal into a superposition. They want to make it exist in 2 places at once. The technical challenges are staggering. Every vibration must be eliminated. Every stray photon must be blocked. Every interaction with the environment must be prevented for long enough that the wave function can spread, can extend, can reach out and embrace multiple positions simultaneously. On Earth, this is almost impossible. The ground trembles, the air carries heat. Even the cosmic rays, those high-energy particles raining down from distant supernovae, can strike the crystal and collapse its state before the experiment begins. But in space, the conditions are different. In space, you can drop the crystal into free fall and let it coast for minutes at a time, untouched by anything. You can cool the environment to temperatures where thermal noise becomes vanishingly small. You can shield the apparatus with lead and aluminum and distance itself, putting hundreds of kilometers between your experiment and the nearest source of disturbance. And that is exactly what they are planning. The proposals have names that sound more like science fiction than grant applications. Macro, for macroscopic quantum resonators in space. Decide, for decoherence investigations in the deep expanse. These are not dreams. These are engineering documents with budgets and timelines, and technical specifications running to hundreds of pages. The researchers have calculated the mass of crystal they can lift. They have calculated the orbit they need. They have calculated the duration of the experiment and the sensitivity of the detectors and the probability of success. And they have calculated what they expect to see. If standard quantum mechanics is correct, if the superposition should form and remain stable, then the crystal will show interference. When the 2 branches of its wave function are brought back together, when the paths recombine, there will be a pattern in the data, a signature that says this object was in 2 places at once. The fringes will be there, the wave nature will be confirmed, and the boundary between quantum and classical will be pushed outward into territory where objects are large enough to see, heavy enough to hold, real enough to feel. But if something else is happening, if some collapse mechanism kicks in at a certain mass or a certain timescale, then the interference will be absent, the pattern will be washed out. The data will show that the crystal was always in one place, that the superposition never formed, that something in the universe forbids macroscopic objects from existing in multiple states at once. This is the test. This is what Einstein was really asking about. The researchers do not know what they will find. That is the point. That is always the point in science. You design the experiment not to confirm what you already believe, but to let nature tell you what is true. And nature in these matters has been silent for a long time, but she may be about to speak. The first missions are planned for the late years of this decade. Small satellites, inexpensive by space standards, carrying delicate payloads into orbits where the testing can begin. The crystals will be launched from the surface, carried through the violence of rocket engines and the shaking of atmospheric transit, then released into the calm of the void, where their quantum properties can be probed. And if those first experiments work, if the technology proves itself, then larger missions will follow. There is talk of sending entangled particles to the moon. Not just any particles, photons of course, because photons are easy to entangle and easy to transmit, but also atoms trapped in magnetic bottles and carried by spacecraft to the lunar surface, where they can be released and measured in conditions that Earth cannot provide. The distance from the Earth to the moon is about 380,000 kilometers. At the speed of light, that is a little over 1 second, and in that second, in that gap between emission and detection, the entangled pair exists in a shared state that extends across the void. The experiments would test the Bell inequalities at scales never attempted before. They would look for any deviation, any hint that the correlations weaken with distance, any sign that the quantum world has an edge beyond which the classical world begins. The predictions are clear. Quantum mechanics says the correlation should hold. The entanglement should survive the journey. The moon should be no barrier to the spooky action. But the predictions have never been tested at that range, and in science, a prediction is just a story until the data comes in. The moon itself would become a laboratory, not in the metaphorical sense, in the literal sense. Researchers are designing instruments that could be placed on the lunar surface, powered by solar panels, communicating with Earth by laser link, conducting experiments that require the vacuum and isolation that only the moon can provide. The environment there is hostile in some ways. The temperature swings from 250 degrees below zero in the lunar night to over 100 degrees above in the lunar day. The regolith is abrasive, fine as flour, charged by the solar wind and eager to cling to every surface. But the vacuum is better than anything we can make on Earth. The gravity is low enough to allow long observation times. And the distance from human activity, from the hum of civilization, from the electromagnetic noise of a technological species, makes it the quietest place in our immediate neighbourhood. Some of the proposed experiments would look for gravitational effects on quantum systems. This is the frontier that no one has yet crossed. Quantum mechanics and general relativity are the two pillars of modern physics, the two theories that together describe almost everything we have ever observed, from the behaviour of atoms to the structure of galaxies. But they do not fit together. They use different mathematics, they make different assumptions, and in the rare situations where both should apply, where gravity is strong and distances are small, the theories give contradictory answers. Physicists have been searching for a theory of quantum gravity for nearly a century. String theory, loop quantum gravity, causal, dynamical triangulations, emergent gravity from entanglement. The names proliferate. The mathematics grows ever more sophisticated. But the experiments remain elusive, because the regime where quantum gravity matters is so far from our everyday experience that no laboratory we can build seems able to reach it, unless the effects are larger than expected. Unless gravity does something to wave functions at scales we can actually probe. Some theories predict exactly that. Roger Penrose, the mathematician and physicist whose work on black holes won him the Nobel Prize, has long argued that gravity causes wave function collapse. His theory, developed with physicist Laios Diossi, suggests that when a mass is placed in superposition, when it exists in two places at once, the gravitational field itself becomes superposed. And a superposed gravitational field, according to Penrose, is unstable. It cannot last. Within a time that depends on the mass and the separation, the superposition must collapse, and the object must find itself in one place or the other. The Penrose-Diossi theory makes specific predictions. It says that a crystal of a certain mass, placed in a superposition of a certain separation, should collapse within a certain time, and that time is short enough to measure. If the theory is right, the space experiments will see it. The interference pattern will be absent, the collapse will have occurred, and for the first time we will have direct evidence that gravity and quantum mechanics interact in a way that requires new physics. If the theory is wrong, the interference will be there, the superposition will hold, and we will know that whatever unifies quantum mechanics and gravity, it is not this. Either way, we will have learned something. Either way, the universe will have answered a question that has been waiting for an answer, since the days when Einstein and Bohr argued in the corridors of conferences, since the days when the founders of quantum mechanics stood at the edge of their own creation and wondered what it meant. Let that settle for a moment. The experiments are not easy. The timelines are long. The funding is uncertain, dependent on the priorities of governments and the whims of budgets. But the plans exist, the technology is advancing, and the researchers, patient as the stars themselves, are preparing. There is something beautiful about this persistence. Science is often portrayed as a series of breakthroughs, as moments of sudden insight when the universe reveals its secrets in a flash. But that is not how it usually works. Most of science is waiting. Most of science is careful preparation. Most of science is building the instruments, refining the techniques, failing and trying again, and failing better, until finally, after years or decades of effort, the data comes in clear enough to say something. The question of whether the moon exists when no one is watching is not going to be answered in a single dramatic moment. It will be answered, if it is answered at all, through a slow accumulation of evidence, through experiments that push the boundary a little further each time, through the patient work of thousands of researchers across generations. And that work is happening now. In laboratories around the world, teams are preparing for the next round of tests. In Italy, in Germany, in Austria, in the United States, in China, in Japan, researchers are cooling crystals and trapping atoms and building interferometers with ever greater sensitivity. The numbers are getting larger, the masses are growing, The times are extending. The record for the largest object placed in superposition is constantly being broken. A few years ago, it was molecules of a few hundred atoms. Then it was molecules of a few thousand. Now there is talk of objects with millions of atoms, objects that approach the threshold where some theories say collapse should occur. Each experiment is a step. Each success is a proof that the boundary has not been reached. Each failure, if it comes, will be a discovery in itself, a sign that something new happens when quantum systems grow large enough. And the moon watches over all of it. Not consciously, of course. The moon is rock and dust and ancient lava, indifferent to the questions asked in its light. But it has been there since the beginning of these inquiries, since Einstein walked under the night sky and wondered about its reality, since Bohr argued that such questions had no meaning, since generations of physicists looked up and asked what it would take to know for certain. The moon has been measured by every photon that ever struck its surface and bounced away. It has been measured by every cosmic ray, every solar wind particle, every gravitational interaction with every other body in the solar system. The moon is entangled with the universe in ways too complex to ever fully describe. Its wave function, if it has one in any meaningful sense, collapsed into definiteness long before humans evolved to wonder about it. And yet the question remains, because the question is not really about the moon. The question is about the nature of reality itself. The question is about what exists independent of observation, about whether the universe is one thing or many, about whether determinism reigns beneath the randomness or whether chance is fundamental, about whether consciousness plays any role at all in the fabric of existence. These are old questions. They are questions that philosophers asked long before physics had a name. But now, for the first time in human history, they are questions that experiments can address. Not answer definitively, perhaps, not settle once and for all, but probe, test, constrain. The experiments tell us that quantum mechanics works. They tell us that the predictions hold, that the correlations exist, that the wave function is more than a mathematical convenience. But they do not yet tell us what the wave function is. They do not tell us whether the moon is there when nobody looks, or whether the question itself is confused. They give us data, and the data is consistent with multiple interpretations, multiple stories, multiple ways of understanding what is happening beneath the surface of appearances. The next experiments may begin to change that. If the collapse theories are right, we will see them fail. We will see the interference vanish at a certain scale, and we will know that something causes wave functions to become definite, something beyond mere measurement, something built into the physics of mass and gravity and time. We will not know what consciousness is or whether it matters, but we will know that the transition from quantum to classical is real, is physical, is not just a matter of ignorance or perspective. If the collapse theories are wrong, if the superposition holds to whatever scale we can test, then we will have pushed the mystery further out. We will know that whatever makes the moon seem definite, it is not the kind of spontaneous collapse that these theories predict. We will be left with the other options. Many worlds, perhaps, where every possible position of every possible particle is realized in some branch of an endlessly dividing universe. Or pilot waves, where the positions are always definite but hidden from view. Or something stranger still, something not yet imagined, something waiting to be discovered in the data that has not yet been collected. Science does not promise answers, it only promises methods. It only promises that if you ask the right question in the right way, nature will respond. The response may be cryptic, the response may be partial, the response may open more questions than it closes, but it will be a response, and it will be real, and it will constrain the stories we can tell. The physicists testing whether the moon exists when no one is watching are not mystics or philosophers, though they think about philosophy more than many of their colleagues. They are engineers of the invisible. They are builders of instruments so sensitive that they can detect the recoil of a single photon, the vibration of a single atom, the subtle shift in interference that says a particle took this path rather than that. They work in the gap between the mathematical formalism and the physical world, trying to close the distance, trying to make the equations speak, and they are patient. They have to be. The universe does not hurry. The experiments take years to design and build. The data takes months to collect and analyze. The papers take time to write and review and argue about. and at the end of it all, the answer is often just another constraint, another limit, another step in a journey that has no obvious end. But they keep going. In basements where the walls are lined with copper to block stray radio waves, in mountaintop observatories where the air is thin and dry and the stars are bright and steady, in orbiting satellites where the silence of space allows measurements of impossible delicacy, the work continues. The interferometers are running, the detectors are clicking, the wave functions are being probed, and somewhere in all of that activity, in the hum of electronics and the glow of computer screens and the patient scratching of pencils on paper, the answer is being assembled, not found in a flash of insight. Assembled piece by piece, experiment by experiment, one data point at a time. The moon is still there, hanging in the sky, silver and serene. And the physicists are still watching, still measuring, still asking. The night is long, but it is not empty. It is full of questions, and the questions are being tested. The universe keeps its secrets, but not forever. Not from those who have the patience to look. And yet there is something else, something that runs beneath all the equations and experiments like groundwater beneath a desert. It is the question of what we mean when we say a thing exists, not whether the moon is there, the physicists are testing that or something like it, but what it would mean for the moon to be there, fully, definitively, in a way that does not depend on anything else. The question sounds simple. It is not. It is one of the oldest questions in philosophy, and it has not been answered. Not really, not in a way that satisfies everyone. The physicists working on these problems are aware of this. They have to be. Because the mathematics they use, the formalism of quantum mechanics, does not speak directly about existence. It speaks about probabilities. It speaks about measurements. It speaks about what you will find if you look. But it is strangely silent on what is there when you are not looking. This is the heart of the matter. This is what makes the question about the moon more than a thought experiment, more than a clever puzzle for undergraduate physics students. It is a question about the nature of reality itself, and the answer, if there is one, will shape how we understand everything from the smallest particle to the largest structure in the cosmos. Consider what it means to say that something is definite. A rock on the ground, a chair in a room, the moon in the sky. We say these things exist, that they have properties, mass, position, colour, shape, and that these properties are what they are regardless of whether anyone is observing them. This is the common sense view, the view that most of us carry through our daily lives without ever questioning it. The rock does not need you to look at it to be a rock. The chair does not wait for your attention to have 4 legs. The moon does not flicker in and out of existence depending on whether someone happens to glance upward. This is called realism in the philosophical sense. The world is real. It has definite properties. Those properties exist independently of our knowledge of them. But quantum mechanics, in its standard formulation, does not quite say this. It says something stranger. It says that before you measure a property, the property may not have a definite value. The electron does not have a definite position until you look. The photon does not have a definite polarization until you test it. The system exists in a superposition, a mathematical combination of all the possibilities, and only when you interact with it, only when you perform a measurement, does one of those possibilities become actual. This is not just a statement about our ignorance. It is not like saying the coin is either heads or tails, but you don't know which. According to the standard view, the coin is both heads and tails, in a sense, until you look. The wave function describes all the possibilities, and the act of measurement, whatever that means, selects one of them. This is where the trouble begins. Because if this is true for electrons and photons, why not for baseballs and cats and moons? The equations do not draw a line. There is no clause in the Schrödinger equation that says this applies only to things smaller than a bread box. The math is the same at every scale, and yet we do not see baseballs in 2 places at once. We do not see cats that are both alive and dead. We do not see the moon flickering between positions in the sky. Something happens somewhere between the quantum world and the classical world that makes things definite, and no one knows exactly what that something is. This is the measurement problem, and it has haunted physics for nearly a century. Some physicists try to dissolve it, to argue that it is not really a problem, that the appearance of definiteness is an illusion or an artifact of our limited perspective. Others try to solve it. to find the mechanism that turns superpositions into definite outcomes. Still others try to avoid it, to reformulate quantum mechanics in a way that does not require the concept of measurement at all. Each approach has its defenders, each approach has its difficulties, and the debate continues in seminar rooms and journals and late-night conversations over coffee, with no clear winner in sight. But the experiments are changing the conversation, because whatever your philosophical position, whatever you believe about the meaning of the wave function or the nature of measurement, the experiments produce data, and data has a way of narrowing the possibilities. The collapse theories, for instance, the ones that say the wave function spontaneously becomes definite, that superpositions decay on their own, that larger objects decohere faster than smaller ones. These theories make predictions. They say that if you build a sensitive enough experiment, you will see the interference patterns fade, you will see the quantum effects disappear at a certain scale. And if you do not see this, if the interference persists to larger and larger masses, then those theories are wrong. Not philosophically wrong, empirically wrong, ruled out by the evidence. This is the power of experiment. It does not settle philosophical debates directly. It does not tell you what existence means or whether the moon is real in some deep metaphysical sense, but it constrains the options. It says, whatever story you tell, it must be consistent with these facts. And as the facts accumulate, as the experiments push further into the borderland between quantum and classical, the space for speculation shrinks. The stories that remain must fit the data. The stories that do not must be discarded, no matter how elegant or intuitive they seemed. The physicists know this. It is why they keep building larger interferometers, why they keep cooling more massive objects to their quantum ground states, why they keep searching for the subtle signatures of collapse. They are not just testing theories, they are testing the boundaries of the knowable. They are asking, how far can we push the quantum description of the world before it breaks? And if it does not break, if the superpositions hold to the limit of our experimental reach, what does that tell us about the nature of reality? Let that settle for a moment, because this is not a small question. It is not a technicality or a footnote. It is a question about what kind of universe we live in. A universe where things become definite on their own, through some physical process we have not yet fully understood. Or a universe where definiteness is, in some sense, created by observation, by the interaction between a system and an observer. Or a universe where definiteness is an illusion, where all possibilities are equally real, endlessly branching into parallel worlds that never touch. Each of these options has profound implications. Each of them reshapes our understanding of what it means to be, to exist, to have a place in the cosmos. And the physicists are patient. They have to be. The experiments take years to design and build. The cryostats must be engineered to hold temperatures colder than outer space. The isolation systems must be perfected to block every stray vibration, every wandering photon, every electromagnetic whisper from the world outside. The detectors must be calibrated to sensitivities that would have seemed like fantasy a generation ago. And then, after all that work, the data comes in slowly. A few photons at a time, a few clicks on a detector, a few data points that, taken together, might say something about the nature of reality, or might just be noise waiting to be averaged out over longer observation runs. There is a kind of faith in this work, though the physicists might not call it that. A faith that the universe is comprehensible, that the patterns are there to be found, that the questions have answers even if those answers take decades or centuries to uncover. This is not the faith of religion, which posits truths beyond evidence. It is the faith of science, which posits that evidence can lead to truth, that the world is not arbitrary, that the laws of physics are the same in every laboratory and every corner of the cosmos. Without this faith, the work would be meaningless. With it, the work becomes a kind of pilgrimage, a slow, patient journey toward understanding, with no guarantee of arrival, but a deep conviction that the journey is worth taking. And the moon keeps rising. It does not know it is being questioned. It does not care that physicists in basements and mountaintops are probing the foundations of its existence. It simply hangs there, silver and silent, following the curve of its orbit as it has for 4.5 billion years. The tides respond to it, the wolves howl at it, the poets write about it, and the physicists measure it in ways that would astonish the philosophers of ancient Greece, in ways that would puzzle even the giants of the scientific revolution. They measure the moon not by looking at its light, but by looking at the principles that should govern its existence. They measure it not by asking where it is, but by asking what it means for it to be anywhere at all. This is the strange gift of quantum mechanics. It has given us technologies beyond imagining: lasers, semiconductors, MRI machines, the digital revolution. And it has given us questions that we are still learning how to ask. Questions about the relationship between the observer and the observed. Questions about the nature of probability and the meaning of chance. Questions about whether the world is made of things at all, or whether it is made of something stranger. Waves of possibility, fields of potential, mathematical structures that only become concrete when they are touched by measurement. The physicists testing whether the moon exists when no one is watching are working at the edge of this strangeness. They are not trying to prove that the moon is unreal. They are trying to find out what real means, at the deepest level the equations can reach. They are trying to discover whether the definiteness of the world is fundamental or emergent, whether it is built into the fabric of physics or arises from something else: interaction, complexity, consciousness, or some combination we have not yet named. Rest with that for a moment. Let the question breathe. Because this is not a question that will be answered quickly. It has already taken nearly 100 years, and it may take 100 more. The experiments will continue, the data will accumulate, the theories will be refined and discarded and replaced, and slowly, incrementally, the outlines of an answer may begin to emerge. Not a final answer perhaps, not a complete answer, but an answer that narrows the possibilities, that closes off some paths and opens others, that brings us a little closer to understanding what kind of universe we inhabit. There is a phrase that physicists sometimes use when they talk about these problems. They call it the quantum to classical transition. It sounds technical, and it is, but what it really means is this: how does the world stop being strange? How does the world of superpositions and interference and entanglement become the world of definite objects and clear outcomes and moons that stay in one place? This is the transition that the experiments are probing. This is the boundary that the physicists are trying to map. And every new data point, every new constraint, every new limit on the size of objects that can be put into superposition brings that boundary into sharper focus. The boundary is not sharp. That is one of the things the experiments have shown. There is no sudden wall where quantum ends and classical begins. Instead, there is a gradual fading, a slow loss of coherence, a progressive entanglement with the environment that makes the interference harder and harder to observe. This is decoherence, and it is a real physical process, understood in detail and confirmed by experiment. But decoherence is not the whole story. It explains why quantum effects are hard to see at large scales. It does not explain why they stop being there. It does not explain, not fully, why the moon has a definite position rather than a smeared-out wave function spread across the sky. This is the gap that the collapse theories are trying to fill. They say that decoherence is not enough, that there must be something more, some additional mechanism that turns the spread-out wave function into a localized object. Gravity, perhaps, the curvature of space-time, the intrinsic randomness of matter at its deepest level. These are the proposals, and the experiments are designed to test them, to see if there is a threshold, a critical mass, above which superpositions cannot persist, to see if the universe has a built-in preference for definiteness, a tendency toward the classical, a hidden hand that guides the wave function toward one outcome rather than another. And if there is no such threshold, if the superpositions hold to every scale we can test, then the mystery deepens. Then we must consider that definiteness is not built into the physics at all, that it is something else entirely, an artifact of our limited perspective perhaps, or a real but non-local phenomenon, or a feature of consciousness that we do not yet understand. These are the options that remain if the collapse theories fail, and the physicists, for all their rigour and caution, cannot rule them out. Not yet. Not until the experiments have spoken. The night sky is patient. It has seen continents drift and species rise and fall. It has watched the slow cooling of the Earth, the gradual brightening of the sun, the endless dance of planets around their ancient orbits. It does not hurry. It does not demand answers on any particular schedule, and the physicists, in their own way, have learned to match this patience. They work in the rhythms of the universe, the long, slow rhythms of data accumulation and theory refinement and experimental iteration. They know that the answers, if they come, will come in their own time. And they keep working, keep measuring, keep asking. The moon is still there. It has always been there, for as long as there have been eyes to see it. But the question of what it means for the moon to be there, that is newer. That is a question that could only be asked after quantum mechanics, after the strange logic of superposition and measurement and collapse had been discovered and explored. It is a question that our ancestors could not have imagined, because they did not have the conceptual tools to frame it. We have those tools now. We have the equations and the experiments and the philosophical frameworks, and we are using them, slowly and carefully, to probe the foundations of existence itself. There is no guarantee of success. The universe is not obligated to be comprehensible. The questions we're asking may not have answers, or the answers may be beyond our ability to grasp. This is the risk that every scientist takes, the gamble that underlies every experiment and every theory. But the history of science suggests that the gamble often pays off. Not always, not completely, but often enough to justify the effort. The universe has surprised us before. It has revealed structures and patterns and laws that no one could have predicted. And it may surprise us again in the data from the next generation of interferometers, in the subtle deviations from quantum mechanics that signal the presence of something new. The physicists are ready. They have been preparing for decades, building the instruments, refining the techniques, laying the groundwork for tests that will push the boundaries of the knowable. And when the data comes in, they will be there to analyze it, to interpret it, to argue about what it means. They will not agree, not at first. That is how science works. The disagreements are part of the process, part of the slow convergence toward understanding. But eventually, if the data is clear enough, if the experiments are replicated and confirmed, a consensus will emerge, and we will know something we did not know before, something about the nature of reality, about the transition from quantum to classical, about what it means for the moon to exist when no one is watching. Until then, the questions remain open, the experiments continue, the night is long and the stars are steady, and the moon hangs in the sky like a challenge and a promise. A challenge to understand, a promise that understanding is possible, and somewhere, in a laboratory you will never see, in a cryostat colder than the void between galaxies, a tiny object is being coaxed into a quantum superposition. It is both here and there for now, and the physicists are watching, waiting to see what happens next. The watching is itself a kind of answer. Not the answer, perhaps, not the final resolution that would settle the matter and close the book, but an answer nonetheless. Because in the act of watching, in the careful, patient measurement of quantum systems at the edge of the classical, the physicists are doing something that the universe has never done before. They're asking it to explain itself. They're building instruments delicate enough to catch the moment of transition, the instant when the quantum becomes the classical, and they are recording what they find. This is new. This is unprecedented. For 4 billion years, the Earth has circled the Sun, and for all that time, quantum mechanics has been operating in the background, governing the behavior of atoms and molecules and photons, and no one has been watching. The rocks did not ask questions. The oceans did not build interferometers. The forest did not wonder what it meant for a particle to be in two places at once. Only now, in this thin slice of cosmic time, has a species emerged that can ask these questions and begin to answer them. And the questions, when you trace them to their roots, are questions about existence itself. What does it mean for something to be real? What does it mean for the moon to exist? These are not idle philosophical puzzles, not the sort of abstract wordplay that can be dismissed as irrelevant to the practical business of living. They are questions that quantum mechanics forces upon us, questions that arise directly from the equations and the experiments and the strange logic of superposition. The physicists did not choose to ask them. The universe chose for them by being the kind of universe where quantum mechanics is true. Let me try once more to give you a feel for the strangeness of this situation. Imagine that you wake up one morning and discover that your house has a peculiar property. When you're inside, looking at the walls and the furniture and the windows, everything is solid and stable, exactly as you expect. But when you step outside and close the door, the house enters a kind of blur. It is not quite there anymore, not in the definite sense that a house should be there. It is spread out, smeared across possibilities, existing in a superposition of states that only collapses back into solidity when you open the door and look inside again. This would be unsettling, to say the least. You would want to understand it. You would want to know why your house behaves this way, what mechanism is responsible, what it means for your house to exist in a blur when you're not watching. This is, in a sense, the situation that quantum mechanics describes. Not for houses, because houses are too large and too warm and too entangled with their environment to maintain quantum superpositions. But for small things, for particles and atoms and molecules, and increasingly for larger objects as well, this is exactly what happens. They exist in superpositions until they are measured, and then they collapse into definite states. The blur becomes the solid. The possibility becomes the actuality. And no one knows why. The physicists who are testing these ideas today are heirs to a tradition that stretches back more than a century, to the early days of quantum mechanics, when the founders first confronted the strangeness of the new theory. Niels Bohr and Werner Heisenberg and Max Born and Wolfgang Pauli and all the others who built the edifice of quantum physics were also troubled by the measurement problem, by the question of what happens when a quantum system is observed. They debated it fiercely in letters and papers and long conversations that lasted into the night. They proposed interpretations and argued over their merits, and disagreed about what the equations really meant. And they never resolved the question, not fully, not to everyone's satisfaction. What they did do was develop a set of tools, a framework for making predictions and calculating probabilities that worked. The framework was phenomenally successful. It predicted the outcomes of experiments with extraordinary accuracy, describing the behavior of atoms and molecules and light with a precision that no previous theory could match. And so, the physicists learned to use the tools without worrying too much about the foundations. They calculated and predicted and built devices based on quantum mechanics, and they left the deep questions for later. Shut up and calculate, as the saying goes. It was a pragmatic response to an impossible situation, a way of making progress even when the foundations remained obscure. But the foundations did not go away. They lurked beneath the surface, waiting to be examined. And over the decades, as the tools became more powerful and the experiments became more precise, the questions began to force themselves back into view. The pragmatic compromise that had served so well in the early years became harder to sustain. The physicists could no longer ignore the measurement problem because they were building experiments that probed it directly. They were pushing quantum mechanics into new regimes, testing its limits, looking for the point where the quantum description breaks down and the classical description takes over. And they were finding that the quantum description held, stubbornly and beautifully, far beyond where anyone had expected it to hold. This is the context in which the current experiments are taking place. The interferometers in the basements and the cryostats in the clean rooms and the satellites in orbit are not just testing whether quantum mechanics is true. They are testing where it stops being true, if it stops at all. They are probing the boundary between the quantum and the classical, looking for the mechanism that enforces the definiteness we observe in the everyday world, and so far they have not found it. The boundary keeps receding, the quantum keeps holding, and the question of what happens when no one is watching remains unanswered. Rest with that for a moment. The question of what happens when no one is watching. It is a question that seems almost childish in its simplicity. Of course the moon is still there when no one is watching. Of course the tree makes a sound when it falls in the forest with no one to hear it. These are the intuitions of everyday experience, the bedrock assumptions that allow us to navigate the world and make sense of our surroundings. But quantum mechanics challenges these intuitions. It suggests that the act of observation is not passive, not a mere recording of what is already there, but active, a participation in the creation of what is observed. The observer and the observed are entangled, bound together in ways that classical physics never imagined. This does not mean that the moon disappears when no one is watching. The moon is far too large, far too massive, far too entangled with its environment to maintain a quantum superposition. The Earth and the Sun, and the cosmic microwave background and a trillion other particles are constantly interacting with it, constantly observing it in the quantum sense, constantly collapsing any superposition that might try to form. The moon is classical because the universe forces it to be classical. The decoherence is too fast, too complete, too overwhelming for any quantum fuzziness to survive. But the principle remains. The principle that small systems can exist in superpositions, that the act of measurement collapses the superposition into a definite state. that there is something deeply strange about the relationship between the observer and the observed. This principle is what the physicists are testing. This is what they are trying to understand. Not whether the moon disappears when no one is watching, but why it does not. What mechanism ensures that large objects behave classically? What draws the line between the quantum and the classical? And is there a line at all, or is everything at bottom quantum? The experiments suggest an answer, or at least the beginning of an answer. Decoherence is real. The environment does interact with quantum systems, does entangle with them, does spread the information about their states across an unimaginably vast number of particles. This process, the leakage of quantum information into the environment, is why we see definiteness where quantum mechanics predict superposition. It is why the moon is there when no one is watching. The moon is being watched all the time by everything around it. The sun pours photons onto its surface. The Earth tugs at it with gravity. The cosmic background fills every corner of space with faint radiation. All of this constitutes observation in the quantum sense. All of this ensures that the moon remains classical. But decoherence, for all its explanatory power, does not solve the measurement problem completely. It explains why we do not see superpositions in everyday life. It does not explain why one outcome occurs rather than another. It does not explain what happens to the other possibilities, the branches of the wave function that describe the alternatives we did not observe. It pushes the problem back, relocates it, but does not dissolve it. The question of what is really happening at the deepest level remains open, and this is where the interpretations diverge. The many worlds view says that all the branches are real, that every possibility is actualized somewhere in an infinite ensemble of parallel realities. The collapse theories say that the wave function really does collapse, that only one outcome is real, and the others are eliminated by some physical process that we have not yet fully understood. The relational views say that the question itself is confused, that reality is not a single objective thing, but a web of relations between observers and observed. Each interpretation has its proponents and its critics. Each makes different predictions, at least in principle, about what happens at the boundary between quantum and classical, and the experiments are designed to distinguish between them. Let that thought hold you gently. The experiments are designed to distinguish between them. This is not philosophy. This is physics. The interpretations, for all their metaphysical strangeness, make different empirical claims. The collapse theories predict that large superpositions will break down in specific ways, at specific rates, through specific mechanisms. The many worlds view predicts that superpositions will persist indefinitely, that no physical process will cause them to collapse. The experiments can test these predictions. They can measure the coherence times of larger and larger objects. They can look for the deviations from standard quantum mechanics that the collapse theories predict. They can, in principle, tell us which interpretation is correct. In practice, of course, it is more complicated than that. The predictions are subtle, the effects are tiny, the experiments are fiendishly difficult, but the principle is sound. There is a way forward. There is a path, however long and winding, toward empirical resolution of questions that once seemed purely philosophical. The physicists are walking that path. They have been walking it for decades, and they will continue walking it for decades more. The instruments grow more sensitive, the techniques grow more refined, the objects in superposition grow larger, and with each advance the boundary between quantum and classical is probed more deeply, more precisely, more thoroughly. The question of what happens when no one is watching is being answered, slowly, painstakingly, one experiment at a time, and what will the answer be? No one knows. That is the honest truth, the admission of uncertainty that lies at the heart of the scientific enterprise. The universe is not obligated to match our expectations. It may turn out that quantum mechanics is complete, that decoherence is the whole story, that the many worlds interpretation captures the fundamental nature of reality, or it may turn out that there is a collapse mechanism, a physical process that we have not yet discovered that ensures the definiteness we observe, or it may turn out to be something else entirely, something that no one has yet imagined, a deeper theory that subsumes quantum mechanics and classical physics and reveals both as approximations to a more fundamental truth. Any of these outcomes would be revolutionary. Any of them would reshape our understanding of the universe and our place in it. The physicists know this. They feel the weight of the questions they're asking, and they keep working, keep measuring, keep pushing the boundaries of the knowable. The night is long as it has always been. The stars wheel overhead in their ancient patterns, indifferent to the questions being asked in the laboratories below. The moon rises and sets, marking the passage of time as it has done for 4 billion years. And somewhere, in a basement or a clean room or a control centre monitoring a satellite in orbit, a physicist is staring at a screen, waiting for data, hoping that this experiment will be the one that reveals something new. There is a kind of beauty in this, a quiet, patient beauty. The beauty of human beings reaching out toward the unknown, asking questions that their ancestors could not have imagined, building instruments of extraordinary delicacy to probe the foundations of existence. The beauty of minds grappling with mysteries that may never be fully resolved, knowing that the grappling itself is worthwhile. The beauty of persistence in the face of uncertainty, of hope without guarantee, of work that may take generations to complete. The moon does not know it is being questioned. It hangs in the sky, serene and ancient, reflecting the light of the sun as it has always done. It does not care whether its existence is classical or quantum, whether its definiteness is enforced by decoherence or by collapse, or by some mechanism not yet discovered. It simply is. And that simple being, that sheer there-ness, is the mystery that the physicists are trying to understand. What does it mean for something to be there? What does it mean for the moon to exist, for the Earth to exist, for you to exist? These are questions that science and philosophy have been circling for millennia, approaching from different angles, using different tools, arriving at different partial answers. Quantum mechanics adds a new dimension to these ancient questions, a new layer of strangeness that demands explanation. And the explanation, if it comes, will change the way we think about reality itself. Consider what it would mean to know, truly know, why the moon is there when no one is watching. To understand the mechanism that enforces classicality, the process that transforms quantum possibility into classical actuality. This would be knowledge of the most fundamental kind, knowledge about the nature of existence, about what it means for anything to be real. It would be an answer to questions that have haunted thinkers for centuries, questions about the relationship between mind and matter, between observer and observed, between the world as it appears and the world as it is. The physicists are not thinking in these grand terms most of the time. They are thinking about coherence times and decoherence rates and systematic errors and calibration procedures. They are thinking about the practical challenges of the next experiment, the technical obstacles that must be overcome, the funding that must be secured. This is how science works, in the trenches, one problem at a time. But the grand questions are there, in the background, giving meaning to the mundane details. The coherence time of a levitated nanoparticle matters because it tells us something about the boundary between quantum and classical. The systematic errors matter because they could obscure a signal from the foundations of physics. The practical challenges matter because overcoming them brings us closer to understanding. And so the work continues, in laboratories scattered across the world, in universities and research institutes and government facilities. The physicists keep pushing. They keep building more sensitive instruments, keep finding new ways to isolate quantum systems from their environments, keep extending the regime where quantum mechanics can be tested. And they keep finding that quantum mechanics holds, that the superpositions persist, that the coherence lasts longer than expected, that the boundary between quantum and classical, if it exists, lies farther out than anyone predicted. This is a remarkable fact. It suggests that quantum mechanics is not just a theory of the very small, not just a description of atoms and molecules and photons. It suggests that quantum mechanics is fundamental, that it underlies everything, that even the moon and the Earth and the stars are quantum systems, just quantum systems that are too large and too warm and too entangled to display their quantum nature in any observable way. The classicality we see is emergent, not fundamental. It arises from the quantum, is produced by the quantum, is a consequence of quantum mechanics operating on an astronomical scale. If this is true, and the experiments increasingly suggest that it is, then the universe is far stranger than our everyday intuition suggests. The solid world around us, the definite world of objects and locations and properties, is a kind of illusion, a surface appearance produced by the underlying quantum reality. The moon is there because quantum mechanics, operating on a cosmic scale, ensures that it is there. But the there-ness is a feature of our perspective, not a feature of the fundamental physics. At the deepest level, there is only the wave function, evolving according to the Schrödinger equation, branching and spreading and entangling in ways that produce the appearance of definiteness without ever actually being definite. This is the many worlds view in its purest form. It is a vision of reality that many physicists find compelling, even beautiful in its simplicity and elegance. But it is also a vision that many find troubling, because it seems to imply that we are not special, that our branch of the wave function is just one among an infinite ensemble, that every possibility is actualized somewhere, and we happen to be the version that sees this particular outcome. It is a vision that raises as many questions as it answers about the nature of probability, about the meaning of personal identity, about what it means for something to be real if every alternative is equally real somewhere else. Let me try to help you feel the weight of this possibility without asking you to accept it. Imagine for a moment that the many worlds interpretation is correct. Imagine that every quantum event, every measurement, every interaction that could have gone differently, has gone differently in some other branch of the wave function. Imagine that the universe is not a single story, but an infinite library of stories, each one as real as the others, each one containing a version of you who made different choices, experienced different outcomes, lived a different life. In this picture, the question of what happens when no one is watching has a strange answer. When no one is watching, everything happens. All the possibilities are actualized. The superposition does not collapse. It merely appears to collapse, from the perspective of each branch. Each observer sees a definite outcome because each observer is entangled with only one branch of the superposition. The other branches continue, equally real, equally valid, but forever inaccessible to that particular observer. The moon is there when no one is watching because the moon is there in every branch. There is no branch of the wave function where the moon has disappeared because the interactions between the moon and its environment ensure that every branch contains a definite moon, even if the moons in different branches are slightly different, have slightly different positions, have been struck by slightly different micrometeors over the eons. The moon is classical because its classicality is enforced by the structure of the wave function itself, by the way entanglement spreads information and prevents interference between branches. This is one possible answer. It may be the correct answer, or it may not. The experiments will tell us eventually if we are patient enough and clever enough to design the right tests. The physicists are working on it. They have been working on it for a long time, and they will keep working on it for as long as it takes. And in the meantime, the moon hangs in the sky, serene and patient, as it has done for 4 billion years. It does not know that it is at the center of a profound mystery. It does not know that physicists in laboratories around the world are asking whether it exists when no one is watching. It simply is. It rises and sets, waxes and wanes, pulls the tides and stabilizes the Earth's axis and lights the night with its borrowed glow. It is a companion, a timekeeper, a symbol of constancy in a changing world. And perhaps that is enough. Perhaps the mystery does not need to be solved for the moon to be beautiful, for the night to be peaceful, for the universe to be worthy of wonder. The questions are part of the beauty. The not knowing is part of the wonder. The fact that we can ask these questions at all, that we have built instruments sensitive enough to probe the foundations of reality, that we have minds capable of grappling with mysteries that may never be fully resolved. This is itself a kind of miracle, a testament to what consciousness can achieve when it turns its attention to the cosmos. You can let that thought settle now. The night is long and the stars are steady, and the moon hangs in the sky like a question that does not demand an answer. It is there, it has always been there, and whether its there-ness is classical or quantum, whether it is enforced by decoherence or by collapse or by the branching of an infinite wave function, it remains what it has always been. A light in the darkness, a companion on the journey, a reminder that there is more to existence than we can ever fully understand. Somewhere, in a laboratory you will never see, in a cryostat colder than the void between galaxies, a tiny object is being coaxed into a quantum superposition. It is both here and there for now, and the physicists are watching, patient and hopeful, waiting to see what the universe will reveal. They do not know the answer, neither do I, neither does anyone. But the asking is its own kind of answer. The reaching is its own kind of arrival, and the moon, ancient and silent, watches over it all, as it has watched over everything that has ever happened on this small blue world, for longer than memory, for longer than history, for longer than the first curious mind ever looked up and wondered what it was. The questions remain, the experiments continue, and the night, as it has always been, is full of light.